cosines and tangents. I'm hoping you have that down because I'm not going to spend any time on that. And if you don't tell anybody. And just go ahead and get it down. That's what I used to do. I was like, oh yeah, I knew that. Shoot. Whoop. 2 hours. Okay, I got it. Really, right? Okay. So, of course, there's no x component of the gravitational force. And you get that the x component of this force should equal the -1 of the other, the tension. That's fine. Let's do the sum of the forces along the y. The same idea. This is what you get. So you set it all up. You get that this is what you should have. And finally, when you put it all together, you should be able to quickly and very nicely figure it out that for my particle, if I choose that one, this should be the electric force acting on it. Simple. I have this slide up. You can look at it. You should have gotten something similar. If you did it on this one, I would expect a few things different, but at the end we come out with the same magnitude, which is all that matters, right? So, any questions on how to set this up? See, how picky are you when you will grade written problems? I will be picky. I want for you, I want explicitly worked out. Are you super duper smart? I'm sure, because you're sitting here. You're so smart and you are brave. Let me just tell you that right now. But I will be picky. Do I need to be so specific? If you're the only one in the world, you don't, but you're not. Somebody else needs to know what the heck is going on in your head. And I can't unless you show me what you're thinking. So I want to see major steps. Official, I want equations written out. I want what cancels, I want beauty. This class is beautiful. You will get to do gorgeous integration. I don't want you to pull stuff out of you nowhere. I want you to tell me where it comes from, right? I will try my best not to do that, because I did have professors who did that all the time. And this, easily shown, is this. Spent 2 hours trying to figure that out. It will happen. I try to pray not to happen. So, any other questions on this? We're good? Okay. So Coulomb's law, we talked about this last class. There's all this stuff about charge that Ben, good old Ben, came up with, and he called them positive and negatives, and you rub something with something, and some charges get transferred. There is different types of charging by contact. What's the other one that we talked about when you ground something? Induction. So different ways of charging an object. Will I ask definitions? No. I won't ask you definitions, but perhaps can I put on the test a problem like the activity 1 we had last class? Yeah, I could. Something easy, not like 10 steps of balls touching and separating each other, because that's kind of ridiculous. But, you know, I would test you on that kind of thing. So what we're learning today is actually we want to quantify that force, because you know it can't just be that easy, right? So we actually want to write a formula, right? This is what he figured out. So Coulomb's law, it was going to take this form. What do the brackets mean? Not brackets, but what does this mean? Absolute value. What does an absolute value of a quantity mean? It's magnitude. So, what does a magnitude of a vector? What is the magnitude of a vector?
Its amplitude?
What is a vector? When I say vector, when you think of vector, what comes to your head?
Like a direction and a force, a magnitude.
If you have to draw it, what would you draw?
An arrow.
An arrow. So in this class, we will think of arrows. There will be arrows going up and down, left and right, that you have to divide into x's, y's, and z's. So yes, it's an arrow. So when I say an arrow has two things, magnitude and direction. This is the absolute value or the magnitude. How do we find the magnitude of a vector that has 3 components, one in the x, the y, and the z? What do we do?
Break it into components?
Yes, it already has the 3 components. So it's like 3i hat minus 2j hat plus 5k hat. How do you find the magnitude of that vector?
Cross dot product? Or Multiply?
Square root of the sum.
The square root of.
The sum of the square.
The square root of.
So root means squared? Is
Is
that?
this no? Is
Alright.
this guy? Is this guy? What is it? Back in the day, triangles, pi. What is it?
Pythagoras.
Alright.
We do the square root of each component squared, right? Okay, good. Okay, so this is how it's gonna look. So let's dissect this. Let's talk about this. I'll show you this. What is this? I had a lot of trouble when I was in your position. Why does it need to be this complicated? And the answer that I got was very unsatisfying, but I learned the truth. It simplifies things later. So instead of calling it just K, which is sometimes called K, it's just a constant, we decided that we need to write it in this way so that it simplifies things later. Very unsatisfying, I know. But this is true. So what is Q1? What do we use Q to do, to represent?
Charge.
So let's say we have two particles, particle 1, particle 2. So the forces between these two particles is, what is Q? BTW? Charge. Yes? What is charge? What is the charge for one electron? That we talked about it yesterday. 1 point.
602 times 10 to the negative 19.
Yes. Let's learn that number. That's a okay. Q1, Q2 over R squared. If you want to guess, this equation looks a heck of a lot like one that you did back in the day that Newton figured out after something fell on his head. Yes. Do you think really something fell on his head?
Never know.
Maybe, man.
Okay.
I heard something that it didn't fall on his head, but instead fell next to him. It was an apple.
That makes more sense. Yeah, what do you think?
Maybe he was
Do you think that's why Apple is called Apple?
Say that again?
Do you think that's why the company Apple is called Apple?
No.
I don't know, just thinking. All right, so Q1, Q2 over R squared. So it looks a lot like it. What's that formula? G M1 M2 over R squared. What does that formula really say? That formula says that there is what? Every object in the universe feels attraction to every other object in the universe. Does that mean that I feel an attraction right now that I can kind of calculate to that chair? Yes, it does. Would I see me like gravitating towards the chair? No. Okay, that's a very good thing. So let's dissect this expression. So this guy, again, no Google, no nothing. In 1736, he just had a lot of time. That is really it. So favorite invention was the theory of the retaining walls back in 1776. And I was trying to do a retaining wall in the back of my house, and it is really kind of complicated. It's not like something you can come up with. Like, there's a lot of physics in it. So I hired somebody to do it. So he did use a torsion balance. Read all about it to show it. Basically was, he had two particles, and if the two particles attracted each other or repelled each other, there would be some kind of rotation that he was able, crazy enough, to figure stuff out just using that. So go check it out. It has a whole explanation. Craig has a very good explanation on it. So, again, pretty cool guy. He came up with this. Nothing better to do than to give you lots of problems in your life. So here it is. So what is this? So the force, the magnitude of the force is all of these. This constant is called constant K. It has this very Kircherson form of 1 over 4 pi epsilon naught, where this number, 9 10 to the 9, newtons meter square over coulomb square, is the magnitude, is the actual constant, the number itself. Epsilon naught, ever so small. Everybody likes epsilon. It's like epsilon. I don't know. Epsilon, it's also called the vacuum permittivity or the permittivity of free space. So my thesis advisor, Jan Lizan, he's like right next to the area where you all are. He's in the same room with Dr. Jan and Ward Plummer, I don't know if you know, so condensed matter. So I had him way back in the day, he taught me my first quantum mechanics class. And so right after this, what you would do after this. And he's just going, epsilon. He always makes so much fun of him. So now you can make fun of me. It is kind of like a little epsilon. Anyway, epsilon, this is the value for epsilon, okay? So we talked about yesterday that the charge 1.602 times 10 to the negative 19 coulombs. Let's talk about SI units. From last semester, you know at least 3 SI base units. The M, K, S. M stands for, what's an SI unit? What's a unit?
A standard unit of measure?
It measures something, right? So base units means that all of the units that come after are derived from those, correct? So the MKS system stands for meters, kilograms, and seconds. So now you will learn that there's another SI unit. The SI unit is actually the ampere. The ampere is coulombs per second. Why is the coulomb not a base SI unit? It's a derived SI unit when you multiply amperes times seconds. Because it's hard to measure how much charge goes through something. It's easier to measure how much charge per time flows through a wire, and you will learn how to do that Ampere's law later on. So it is harder to measure actual Q, so we measure it indirectly, okay, after calculating these. So just know, base unit is the ampere, and the coulomb is an SI unit, but it's a derived SI unit, okay? So, how neutral are atoms? So last class I told you that everything here is neutral, and that this crazy attraction or repulsion results actually from a charge imbalance, but it's a teeny tiny charge imbalance. How much really is the imbalance, and what amount of force are we really, really talking about? So, if we remove one electron from one electron out of every million atoms in each object, what is the force between the two objects? The objects that I'm talking about is two random objects, a table, two tables that weigh, no, table cannot be because the table cannot weigh 1 gram. So let's talk about an atom, okay, or whatever it is, separated by 10 meters. So if we just take just one electron out of every 10 to the 6 that there are in that atom, what is the force separated 10 meters apart? What is the force that each one of those exert on each other, okay? So, how do we figure that out? You have something similar in your homework, so let's learn how to do that. In this case, Avogadro's number of particles come into play. What is Avogadro's number of particles and what does it mean? 6.02 times 10 to the 23 atoms in what? In what?
1 unit?
In a mole
Yeah.
of a
Substance.
substance. Okay? So let's learn how to work with this. Why do we need to work with this? Because in order to use F is equal to K, Q1, Q2 over R squared, you need to find Q. Well, what the heck is Q? Q is the charge. How are you going to know the charge if you don't know how many atoms are there? Right? Each electron has 1.602 times 10 to the negative 19 coulombs of charge. So if I give you a mole of H2O, you're going to have to do chemistry for a few seconds to figure it out, okay? So first we have to, let's say the objects are made out of carbon, which is a very good assumption. And so then they should contain, let's say, 1 gram, okay, so what is the molecular mass? 1 mole of carbon has 12 grams, right? So again, I want you to be neat, I want you to be smooth with conversions. Why? It helps you make sure you're multiplying or dividing the right way. So again, the grams cancel with grams, and you're left with moles of carbon. So now I need to figure out how many particles in 1 mole of carbon. So I proceed to multiply this number by 6.0 times 10 to the 23 atoms. Yes? Once I do that, I now know my object has, if it's made out of carbon, whatever it is that weighs 1 gram, it has 0.5 times 10 to the 23 atoms. Again, we're talking about a humongous number. I don't even know what that number means, right? That's how things start. So, now that you did a little bit of chemistry, we need to figure out the charge of each object. Yes? So how do we figure out the charge of each object? I have that many atoms.
Didn't you say like for every million? So
Right, because I took 1 out of every million, so I gotta make sure I take care of that. I didn't take all the atoms, I just removed 1, correct? So first, I gotta be careful. This is very important. 1 atom out of every million times however many atoms I have times the charge, right? The charge of a proton equals the charge of an electron, which is 1.6 times 10 to the negative 19. So now I am ready to figure out the total charge in this object. Total charge in this object made out of carbon that weighs 1 gram is 0.8, not in this object, in this electron removed. 0.8 times 10 to the negative 2 coulombs. So now I am ready, again. Everybody knows what this means. It's not microcoulomb, milli, right? Yeah? Okay. So, let's calculate the force. F equals 2K, Q1, Q2 over R squared, right? So, do we know everything we need? We know everything we need. Everything we need, this is K, Q1, Q2, they're identical, yes, over R squared. They're separated by 10 meters. Remember, we need to use, here everything is SI. So if I were to give you this distance in centimeters, you have to make sure you have to convert it to meters, correct? We are using MKS units throughout, right? So when you plug that in the calculator, again, I want you to be smooth calculating these numbers. I do not like scribbles. I like units. I like what cancels, and I like units everywhere. Why? This helps you make sure you're doing it right, and this helps me greatly. And I will be so impressed. I will write a thank you note on your test. And if I'm not impressed, I will call you to my office and ask you what the heck are you doing, because I cannot read this, any of this. Okay. So if I write everything, I'm left with this. What does this number mean? So I tell you what this number means. Somebody tell me, what does the number, how do I find, what the heck is 5,000 newtons? Okay, what can we do with newtons?
we could break it up into what Newton means.
Yes, what, okay, make it, what am I'm looking for something. Make it meaningful. Okay, I tell you something meaningful. The average force that you exert when you open a door, 1 Newton. That's a lot. That's kind of meaningful. F is equal to mg. Yeah?
Okay.
So in pounds or in kilos, if you take that number and you divide by 9.8, I can get kilos, I can get pounds, so I can get kind of a force, I can get kind of like how many pounds of a, like, you know, like make it meaningful. So, okay, so what I'm saying is, that's a big number. And I just removed 1 out of 10 to the 6.
Right.
So this attraction, it is crazy. This force of attraction or repulsion, it's a minor imbalance. It's not like you're getting a flow of electrons taken out. No, it's just 1. 2 creates this crazy effect on another one, right? Take home message. That's what I want to say. So, vector form. You will not only calculate the magnitude of forces, but you have to tack a direction to it. How are you going to do that? So, your book, this is your job. Your job is to read. I'll give you pointers, but you have to read. What do I like for you to do? I like for you to do the examples on the book. We're using Walker, H.R. Walker mainly. Crane is very good, so I will supplement with Crane. But Walker has a lot of intuitive, good examples. I want you to do those examples. That is the best way you learn. For me, by watching me, you get pointers, but if you really want to learn, you got to do it. You got to strap down to a chair and just do it.
Okay.
So, give you the basis. Particle 1, particle
they're polar opposite?
They're the same.
Oh, okay, my bad. Wait.
I don't know. Can you wait for anything?
Well, I see that arrows are in complete opposite directions, right? So
Yeah, so the net force might be in two completely opposite directions. So these particles could repel each other, these particles could attract each other. Either way, you're going to have to figure that out, right? If the particles are on the same side, they will repel each other. If they're on the opposite sides, they will attract each other, right? Kind of like you did the free body diagram for the homework problem. So in either case, whichever case comes out to be, F12, the force on 1 due to particle 2, should be 1 over 4 pi epsilon naught, Q1, Q2 over R12 squared, and this is needed. This is the R hat 1, 2. These will tell you the direction of the force. So again, if the forces, if the direction, if the particles have the same sign, then it is directed away. If it had opposite signs, then it is directed towards the other particle. So, more than two particles. What do we call this? Summation, but it's a super.
Position.
Yes. It's called superposition. You'll see this all the time. You actually saw it last semester too. And the principle of superposition is pretty crazy if you really think about it. What this is saying is, if you have 25 particles, I just took 25 particles. I'm not going to write 25, but I'm going to write this many. And I want to find the force on this particle. It is enough to look at 2 on 1, 3 on 1, 4 on 1, 5 on 1, 6 on 1, and add them up. So it's like the effect on this one from this one doesn't matter when you're calculating the force on this one.
But that's
It's
only,
not all that obvious.
that would only be for instantaneous though, because after that.
Yes.
it's everything else.
Yes. And this only applies, FKQ1, Q2 over R squared only applies to point particles. It does not apply to what's coming, which is like a line of charge or a ring of charge. Oh, come on. So anyway, this is the easy stuff, and the particles are, you use the principle of superposition D. Is this going to be on my test? Yes, it's going to be problem 1, written problem 1 on your test. I will give you a distribution similar to the homework, similar to the activity problem we will do today, in which you would have to draw vectors, break them into components, add them up, and calculate the net force acting on one part. Does that sound fair? Okay. So let's do a few examples. So I have two tiny conducting spheres. Each sphere has a charge of negative 20 microcoulombs and positive 3 microcoulombs. They're separated by a distance of 2.5 centimeters, and I want to calculate the magnitude of the force each sphere experiences, and is it attractive or repulsive? So simple example to show you how to use this. So again, this is the very first step. The very first step, we go force KQ1, Q2 over R squared. These will calculate for us the magnitude of the force. So, here we go. K is a good old K. Would I expect you to memorize K? No. But it is a pretty number. 9, 10 to the 9. What's the radius of the Earth? 6, 10 to the 6. Those are good numbers to know. Okay, so Q1. Let's calculate the charge on Q1. Calculate the charge on Q2. Convert the radius to SI units. This is what we use. So the charge on Q1, again, multiply this many coulombs, again. Coulombs is the SI unit. It's not microcoulombs. So we got to make sure we know. We got to work with coulombs and we got to work with meters. And put it all together, and I get, so this one, meters squared, I get 15,000. Is this, so 15,000, what is 15,000? Is it a magnitude or is it a vector? Look at the expression that I wrote up there. It's a magnitude, correct? So now let's tap on a direction. You don't know where these particles are, so you cannot tell me. By the way, last semester, did you use X hat or I hat? For unit vectors, you use I, J, K. Okay. attractive? Why would you say it's attractive?
They're opposite.
Because they're opposite sides. There, right? Okay. So, if we touch two spheres, we touch them together, and then place them back 2.50 centimeters, then what is the force between them? Again, question, is it attractive or is it repulsive? So what happens when we touch the two spheres together? There's going to be a flow of electrons from one sphere to the other. Until when?
Equilibrium.
Until they reach equilibrium, which that basically means what?
No charge.
They have the same charge. So right
Yeah.
now, give me a number for the amount of charge that each sphere will have.
0? Wait.
No.
Oh, wait. Oh, yeah.
So one has negative 20 microcoulombs. Come on, write it down really quick. One has negative 20 microcoulombs. And the other one has how much? Plus 53 microcoulombs. So one has an excess of electrons, the other one has a lack of electrons. So electrons will flow from where to where?
It's gonna flow
Correct,
from the.
until what happens? They have the same charge. So tell me now, you did this activity last class, you gave it to me, right? So you know how to do this. What is the charge that each of these must have when I separate them now?
33? Wait. 33.
What do you do? 53
Minus 20.
minus, right? And then how much is 53 minus 20? 33, but 33 is shared, correct? When you separate them, it's 33 divided by 2.
Okay.
Yeah? Okay. So, agreed. So, when we touch them, separate them, blah, 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 we got it. So, Q1 must equal the charge on sphere Q2, which is now 33 divided by 2. Again, we convert to coulombs. This is how many coulombs of charge on each sphere. Do we agree? Microcoulombs cancels with microcoulombs. We've got coulombs left, and then now we go ahead and we plug them in here. Q1, Q2 over R squared. Tell me now. Tell me now. It's not coming out, but fine. Is it attractive or is it repulsive? What is it? It is repulsive. Why? Because now they have the what?
Positive charges, but
They're the same charge.
Yes. See how crazy that is? I like this stuff. Fine. I don't like